I'd like to introduce myself. I'm Catherine Saar, and I'm the host of SF Pug, and this is our April meetup. Before we begin, the meeting is being recorded and will be posted on YouTube afterward. Everyone who speaks during today's event will be part of the recording. We will do Q&A both during and at the end of the presentation. If you choose to ask a question, your voice and image, if you have your camera on when speaking, will be part of the recording. However, we do ask that you please mute your microphones and turn off your cameras during the presentation so that we can focus on the presentation being given. If you're using the most recent version of the app, which we do recommend, you can use the raise hand function to join the queue. If you're using an older version of the app, which does not have this function, please use the chat to let the organizers know you would like to ask a question, and they'll add you to the queue. The organizer will let you know when you're next in the queue, so you can be ready to unmute your microphone and ask your question. If you do not want to be part of the recording, the organizers can convey your question to the speaker. In that case, please type out your question in full and let the organizers know you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page on Meetup, which we are monitoring during the presentation. SF Pug, Bay Area Postgres, is a PGUS affiliated user group, and I am a volunteer for PGUS. And SF Pug is sponsored by PGX, and I work for PGX. And without further ado, here is Tomas Vondra with Where Do Performance Cliffs Come From? There we go.
Okay, so can you see my slides, I guess?
Yes, looks good.
Cool. Okay, so I think we are ready to start. My name is Tomas Vondra. I do work for Microsoft. I'm a long-term Postgres contributor, developer, and also a committer. And I mostly work on the open source PostgreSQL code. And first, before I get into the talk, a couple slides. Okay, I don't have a slide about me, but the contacts are there, right? You can send me an email if you want to have a chat about Postgres. I do have a slot on my schedule for so-called office hours. I'm also participating in the community hacking and mentoring programs, so I can help you with your patches and so on. And this talk is divided into roughly 4 sections. The agenda is on the screen. After each section, I plan to take questions, if you have any, of course, right? So I don't want to leave the questions until the very end of the session because that's just confusing. It's difficult to keep track and answer questions from a long time ago. So today I'm going to talk about performance cliffs, which I think is like a serious problem many people face in their when they are using Postgres, even if they may not actually realize that. And I will try to explain it's kind of like, it's a problem that is inherent to cost-based query planning, query execution, but also, so it means it's not specific to Postgres, it's like a general issue. And I will give you a couple simple examples to demonstrate why this happens, and also share a couple of ideas how you might actually mitigate that. I don't have a perfect solution yet because it's a very broad class of issues, but hopefully this might help you to at least understand why it happens and what you might do about that. And I will, at the very end, I will share a couple slides with references to research. It's a very active research topic, so there's a chance that we'll get some patches in the future improving the situation. So what are performance cliffs actually? Well, there is no clear definition of what that actually means, right? Different people define that in different ways. I usually mean that it's a sudden change in performance, kind of like abrupt thing. It unexpectedly happens. And it's a class of performance or maybe rather robustness issues. It's very common. It happens all the time, even if it's kind of like hidden, and it affects cost-based planning. It's like inherent to that. And in the next couple of slides, I will explain like why it actually happens and what you can do about that. But I don't have any like promises. There is no silver bullet to fix that. And okay, so to give you a very simple example of performance cliff. Imagine you have a query which is just selecting data from a table, right? And you have a parameter A which matches 1,000 rows, and it runs in 1 second, right? Fine. It might be an index scan or a sequential scan, whatever, doesn't matter. Now imagine you have a different parameter, like different value for the parameter. In this case, it's a B, which matches one more row, like 1,001 rows. So what would be the expectation? Like, how long would you expect that to take, right, the query? I would expect that it's going to be roughly 1,000 milliseconds, right? Roughly the same, because it's a minor change in the cardinality in how many rows it matches. And maybe that's true. Maybe that will actually run in 1 second. But it might also run in like 10 seconds, like an order of magnitude longer. And it's definitely unexpected, right? Because it doesn't increase proportionally to the change in the parameter, in the selectivity. So this is what we call like performance cliffs. But it's also about why it actually happens, right? Not each decrease of performance is a performance cliff. So there needs to be some sort of like discontinuity, right? Like sudden step change. And usually this happens because we do flip between different execution strategies, right? So for the example before, maybe we switched from, say, sequential scan to index scan, or vice versa, or something like that. And this usually happens at runtime, right? It might be that one row triggers a lot of additional work. It might be that suddenly a hash join or hash aggregate starts spilling to disk, or instead of sorting in memory, we suddenly start sorting on disk, things like that. And I mentioned at the beginning, I mentioned like cost-based query planning, and that's another sort of like changing a different execution strategy, right? The whole point of query planning is to pick an execution strategy, and if you change the input parameters, that may result in a different execution plan. And maybe the different execution plan was not like the best one. So in which case you will see a performance regression. I will show you in the following parts a visualization to understand why these issues happen with cost-based planning. But in the next section, I want to show you like a very simple, actually practical example of runtime decision affecting the causing a performance cliff. But before I get into that, I think we have a time for the first questions, if there are any. Are there any questions? If not, I will just continue.
There's nothing in chat.
Okay, cool. So hopefully that means it was clear enough. So I'll give you a simple example of a performance cliff because of change in execution strategy, right? So imagine you have a simple table, right? It's a table which is called text. It has a single column, also a text, and you insert, I don't know, I think there's like 10 million rows, right? That have, each row is a string with a very long prefix, just A, and then something random. So this means the table is roughly 1 gigabyte of data. And all the values share the same prefix, which means that it's really difficult to actually compare the individual values, right? This is constructed example specifically to demonstrate like a performance cliff, right? So maybe you wouldn't see exactly this, but what matters is that the comparisons are expensive. And then we will do a query, which is at the top, which is a query with an in condition, which has like a list of values, right? And in practice, you usually have only a handful of those, but I have also seen queries with like thousands of values, right? Typically, that happens in like a generated queries. Anyway, let's say we have a very simple query which has only 9 values in the list, right? And on my laptop, this took about like 1 second, 1,000 milliseconds to run, right? Because I think I didn't have any index there, so this was like a sequential scan, right? There was no index, right? I didn't create an index, so this needs to actually scan the 10 million rows, and for each row, it needs to check this condition. And that's a fair amount of work. It takes like 1 second, right? Now, let's assume that we remove one of the values, right? Instead of 9 values, we will have just 8 values in the list. So how long would you expect this to take? I mean, like, you have less work to do for each query, right? For each row. So I personally would expect this to take like less than 1,000 milliseconds, right? Maybe 900 milliseconds, right? Proportional to the change, because we have only 8 values instead of 9. But in reality, this actually takes like twice as long, right? This takes actually double the time that we needed for fewer values. For more values, right? So that's definitely counterintuitive, right? Why does it happen? It happens because we flip between 2 different execution strategies, right? When evaluating the condition, we have like 2 strategies. For short lists, we do a simple linear search, right? We just walk the value one by one, and we compare that to the value from the row. And then for longer lists, we build actually a hash table, right? Because it's like checking 1,000 values would be very expensive. So it's much faster to do like a hash search. But at some point, you need to flip between those, right? You need to decide, like, it's either a linear search or sequence or hash search. And we do that at 9 values, right? So the first query actually did a hash search. After we removed one value, we are starting to do a linear search. And the problem is that the value, the threshold 9, is kind of like hard-coded, right? It doesn't reflect the actual cost of the operations. We don't have a good way to track that in Postgres because it's specific to data type. That's one thing, right? It's going to be different for integers and for strings, like here, but it's also dependent on the actual values in the column, right? So a string without the long prefix wouldn't probably have this problem. So it's impossible to know this in advance. So we do make mistakes like this. And maybe you will not have problems with in-lists, right? Because you will have like short values or fewer items or something like that. But it's a generic problem. It's definitely not the only runtime decision like this that we actually do have. I already mentioned a couple that happen in different operations in the execution plan. Like, for example, sort may happen in memory, or we start spilling to disk. The same thing applies to hash join, hash aggregate, and so on. Those are all runtime decisions. We do estimate that during planning, but then at query execution, that actually can happen. We can change the decision, right? Another great source of like performance cliffs is like just-in-time compilation. Not necessarily because of the execution itself is expensive, but because compiling the expressions is actually quite expensive and may easily be fairly useless for that particular query, right? So you might have a query which runs without just-in-time compilation in a second, and then suddenly we start doing just-in-time compilation. It takes 10 times longer, right? Because just like we are using LLVM and it's fairly expensive compilation and optimization. So we can improve this, of course, but it's a generic problem. So any questions about this? I guess no. So now I'm getting to the really interesting part of this, which is about actually the cost-based planning, cost-based optimization, and how it is related to performance cliffs. And for that, we need to understand that cost-based planning is actually about making decisions, right? The database has a significant number of different ways to execute queries, right? It can do for individual scans, it can do index scan, bitmap scan, and so on. Then it can join the tables, the relations in different ways, and so on. And how the optimizer picks between those different strategies is by calculating something we call a plan cost, which should be, some sort of a measure of the amount of resources used by that particular plan, right? Resources means like amount of CPU, I/O operations, and so on, which is based on the assumption that if a query plan uses more resources, it's going to be more expensive, like the cost is going to be higher. And if it's also using like more resources, it's going to be more expensive to execute in time, right? It will take longer. So the assumption about cost is that it's kind of like monotonic and continuous with respect to selectivity, right? So for example, index scan that matches 1,000 rows is going to be cheaper than index scan that matches 10,000 rows on the table. And so on, right? So that's kind of like the assumption about cost. And for the purpose of this talk, we assume that the estimates are correct, right? You can get like a lot of performance issues because of incorrect estimates, which just means the database is making the decision based on incorrect data, right? It just doesn't know, it can't actually calculate the cost properly. So that's just something we will assume doesn't happen, right? We assume that we actually do know the costs and the estimates like reasonably well. And I will visualize the cost based on selectivity, right? So how do you do that? For example, for a bitmap heap scan, we can force the query plan to use a bitmap heap scan, and then you can specify a condition for which you know the selectivity, which in this case, I know that there are 10,000 distinct values, and I know that a condition between 100 and 200 that just matches like 1% of the table, right? And based on that, I know that if I look at the execution plan, I know that 1% selectivity means 24,000 cost. And I can also do explain analyze, and then I will know that 1% means 72 milliseconds, roughly, right? And I can do this for different conditions, like different ranges. And I can build a chart, like for 100 different selectivities, right? And I can do a chart like this. And you can see that actually it is smooth, it's continuous. There are no like step changes in the query, in either the cost or duration. It's almost monotonic, right? There is a small decrease in the cost, which I assume is based on, is due to some rounding or like errors or something like that, but I will ignore that. And you can see that also the cost and the duration actually correlates, right? It's not perfect because you can see that the gradients are different, and initially the cost actually increases very, very fast compared to the duration, but nevertheless it's smooth, it's correlated, and that's what we want from a cost estimation. And now I will show you, I mean, like, I said that this is like very smooth, it's perfectly nice, but I also mentioned that the performance cliffs are about like step changes, right? Like abrupt changes. So where does it come from? Well, this is just like one execution strategy, right? We forced to do a bitmap scan in this case. But the database needs to pick from different execution plans, right? It would need to, for a simple select like this, it would need to decide whether a sequential scan, a bitmap scan, and an index scan, if there is an index on that column. And I will show you how that actually causes performance cliffs. So this is actually a table that I will use for this example. Again, it has like, I think 100 million rows or something. And each page has 59 rows, all with the same value, right? So there is no difference between selectivity of values of rows and selectivity of pages, right? If you have 1% selectivity, it also selects 1% of pages. The table has 13 gigabytes and 10,000 distinct values, right? Like each page has like values between 0 and 99,000, I think. And then we have also an index on the table, right, or on the column, and we will do the queries that I shown before, like the range conditions with different selectivities. And if you plot the costs, right, what the database thinks is the cost of the conditions, you will get a chart like this. This is I want to make it clear that this is log scale on both the x and y axis, right? And the values on the y-axis are, that's an arbitrary value, whatever the database uses for the cost. And you can see that most of the interesting things actually happen around like 1% selectivity, right? That is where the costs for the different execution strategies actually intersect. And that means that one of the execution strategy becomes like cheaper and more efficient than the other, right? So up to like 1%, the most efficient strategies are either bitmap index scan or index scan. It's difficult to say, right? And then above 1%, the database thinks that roughly the sequential scan and the bitmap scan are going to perform roughly the same, right? The cost is very close. And now, but this is the cost, right? This is what the database believes about like how much resources those plans will need. So what if we actually, instead of a cost, if we plot the duration for this table? And you will get something like this. And there are, if I flip between those two slides, you can see that it's like very, very different, right? So the database is making decisions based on this, but the actual behavior is this. And the first thing that you should notice is that the plans do not actually flip, do not actually intersect at 1%. They do actually intersect at like 27%, right? This is log scale, so it's not obviously clear, or it's not obvious that it's 27%, but that's what I measured. And the other thing is that you can also notice that the bitmap scan actually happens to be much faster than index scan, right? In this case. So this is the source between this is why the performance cliffs happen, right? Because the database thinks that it will get much faster execution from sequential scan once it crosses like 1%. But in reality, it actually gets much slower performance, like much worse performance. So to demonstrate that, this is actually the example, right? The first query that has a selectivity just below the threshold, right? So the database picks the bitmap heap scan, and you can see it matches like 1.293 millions of rows, right? So it's like 1.3% selectivity. And it runs in about 400 milliseconds. And then we do the smallest possible step, which is just like make the range a bit wider. And it selects by less than 100,000 rows more, like just above 1.3%. And suddenly it takes like 11 seconds, right? Which in this case, it's, I don't know, 20 times longer. So that's not great, right? And this is a clear performance cliff. So any questions about this?
And there's nothing in chat.
Okay, so either I'm extremely boring or making it very clear. So anyway, mitigations. So what you can do about this? Well, I think after looking and thinking about this for a long time and reading a lot of papers, is that I think this is kind of like inherent to cost-based planning in general, right? Because you will never fix this during planning. We are doing planning based on very approximate representation of the data, right? I mean, the statistics is like 1 million times smaller than databases, right? Than the actual data. It just approximates the data distribution. And the costing itself is also very simplified, right? We do not know a lot of information about the data. I mean, we do not even know which parts of the data is currently in memory and something like that. So we are just assuming a lot of things. And we are making decisions based on this incomplete data, right? There is a well-known researcher, Gets Greffe, who says that choice is confusion, right? Like as soon as you are, as you have to decide between different strategies, that's just a recipe for disaster, right? And we are adding more and more ways to execute a query, right? So that's just making it's just making the life harder for the optimizer. So what are the options here? I mean, we will never fix this at the query planning. I mean, I have implemented the extended statistics and that helps, but even then, that's just like a very limited improvement. It will always be just an approximation of the data, right? So first thing is that you can do some tuning, right? You can make the cliff smaller. You will never perfectly align the two places for all possible plans. It's just not possible, right? But you can make them closer, and the performance cliff is proportional to, you know, the distance from the optimal flip point. So if you make them actually closer, you will make smaller mistakes in calculating the cost, and therefore you will also make like smaller mistakes in terms of, you know, the difference in duration. So maybe it wouldn't take the same amount. You will never align that perfectly, but instead of 20 times slower, it will be maybe twice as slow, right? Only, which I think is reasonable. Or maybe make the flip actually cheaper, right? So if you are doing large sorts, and those sorts happen on disk, you probably can get a better storage that is faster for this and you don't need to make it persistent, right? Because those are ephemeral data. You can lose the data if the database crashes, for example, right? So you can reduce the impact of the performance cliff. But really, well, I mentioned that you can tune the cost to actually make the two places where the cost flips and where the actual iteration flips. You would do that by tuning the cost parameters, and it's difficult to actually give advice about how exactly to tune this. But most of the time, just tuning some of the basic parameters like a random page cost and so on is sufficient to improve the situation. I don't think there is a chance to actually make perfect parameter values. It's not possible. It's not possible to do that for all the queries at the same time, right? Because each query does something slightly different, right? It just needs to happen close enough. And at the beginning, I also mentioned that there are a couple interesting ideas how to actually improve the situation. And most of them are actually not about the query planning part, but about making the query execution, once we actually pick the execution strategy, more robust and less sensitive to abrupt changes like this, right? So, for example, imagine that you only do sequential scans, right? You do not have index scans or bitmap index scans. The duration of sequential scan is very stable. It doesn't really matter how many rows in the sequential scan, match the condition, right? So if you only did sequential scan, it would be very slow, but also very, very stable. And there are other ideas how to execute queries. Instead of just doing the index scan and so on, there are things like a smooth scan, for example, which kind of morphs between different execution strategies at runtime. Instead of using a fixed execution strategy, this adapts to the actual pattern in the data, and maybe unexpected selectivities and so on. It's better at handling estimation errors or so, for example. So of course it's a trade-off between performance and robustness, right? You make it slower, but also you get smaller performance cliffs, or you eliminate the performance cliffs, and that can be better and perfectly acceptable in production workloads, right? You may need more hardware, but then you will not get as many calls for support. So I will actually link a couple of the papers that I think are really interesting. I've been experimenting with some of those for like proof of concept patches and so on. The first one is like profile of Getz graph, which I think is interesting to read because it presents this concept of like robustness and importance instead of chasing like the higher and higher throughput numbers from like random benchmarks, assuming that everything's go fine with like query planning and so on. And asks the question if maybe robustness is something we should consider more. And then there's like two different execution strategies for different parts of the query plan. The first one is the smooth scan, which kind of like replaces the usual index scan and sequential scan and index scan. Kind of like instead of having three different options, it just does a smooth scan, which kind of like morphs between those at execution time. And then there's a similar idea for a join, which instead of doing like one, like a nested loop, which is great for certain types of queries, and like merge sort or hash join, merge join or hash join, does a single algorithm, which again does a lot of decisions at execution time and so on, and should be more adaptive to different data distributions and so on. And unrelated to the topic, I think there is a really nice source of pointers to other research, which is something which I think is called Dachstuhl seminars, which is like every couple of years there's like a symposium or something of researchers discussing different areas of database research. And one of those is related to robustness and performance in database query processing. And for me, it was like a really nice source of links to papers in this area of like research. So if you don't know which paper to read, I think this is really good overview of good papers. And that was the last slide I had prepared. So I hope it was interesting. Are there any questions?
There's actually a question in chat. Rustam has asked, in your opinion, will it be anyhow beneficial to plug some AI/ML based solution into the planner?
I personally am very skeptical about like AI, right? Especially in this context, because we have been using AI for a long time, like machine learning before the recent hype, and I think it does help in a limited definition of helps. It definitely can help us learn from existing data, right? Like past executions, for example, right? I'm a bit skeptical about just plugging in something which is like labeled AI and that will magically fix all the problems. I think it's important to understand like why it's happening, and there definitely are things that we can learn from, for example, from past executions, right? Like corrections and like have like a feedback from that into the planner to make better estimates for the future and stuff like that. But I don't see that as a silver bullet or something. I think it really depends on what exactly that means. I don't know if that answers the question, but.
Do we have any more questions? Anybody? Well, thank you, Tomas. That was a great talk. Lots of really good information in there. And thank you for putting up the slides and everything, especially at the end. That gives us a lot of information. So going forward, thank you to PGUS and PGX for sponsoring. Next month, we do not have a speaker. We will be traveling, but we will be back on Tuesday, June 10th for Syncing Postgres into the Client with James Arthur. Upcoming conferences, PG Day Chicago is April 25th. PGConf Dev will be May 13th through 16th in Montreal, Canada. PGConf US, formerly PGConf NYC, will be in September 29th through October 1st in New York City. We will send a link by email when the video is ready, and you can watch our social media. You can find us on LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. We're always looking for speakers, so if somebody you know is interested, please contact us through Meetup. And it looks like we've got a couple more comments. Quinn says, fantastic talk, great job, and a complicated topic, very clear. And Pete DeVisser said, thanks, good talk. And it was a great talk. Thank you so much, Tomas.
Yeah, happy to be here.
Perfect. All right. Thank you so much, and we will see you all next time.